Hi, good day. So let's have this topic. This is for the determination of the general solution of homogeneous equations. Let's have this case. A homogeneous linear differential equation or homogeneous linear equations with constant coefficients with the auxiliary equation distinct roots. So we have, I think, three cases for homogeneous linear equations. So that is the first one, distinct roots. Later on, we are to discuss the repeated roots and the imaginary roots. So any linear homogeneous differential equation with constant coefficients, so our coefficients are a sub o, a sub 1, a sub n minus 1 up to a sub n. Okay. Then the right side should be equal to 0 for homogeneous differential equation. So we can rewrite this expression to a shorter one, that is the f of d multiplied by y equal to 0. So we're in basically f of d is a linear differential operator. So if m is any root of the algebraic equation, then we have f of m is equal to 0, since again m is a root. So we can rewrite the linear homogeneous differential equation as f of d multiplied by e raised to m times x. So which means, we continue, which means the value of y or the equivalent of y is equal to e raised to mx is a solution of the equation f of d times y equal to 0. So the equation f of m equal to 0 is called the our auxiliary equation. Associated with this, again, this expression is the linear homogeneous differential equation, or simply written as f of d multiplied by y equal to 0. The auxiliary equation, let us continue. The auxiliary equations for, again, this expression is for the linear homogeneous differential equation, is of degree n, let its roots be, so the roots, possible roots, m1, m2 up to mn. So if these roots are all real and distinct, then we can write the solutions as, for example, for the first root, that is y sub 1 equal to e raised to m1 times x. For the second root, y sub 2 is equal to e raised to m sub 2 times x up to the nth root, that is y sub n, e raised to m sub n times x. Or if these roots are linearly independent, we can write the general solution at once. So we can have the general solutions or the general solution as y equal to c sub 1 e raised to m1 x for the first root, plus c sub 2 multiplied by e raised to m sub 2 times x up to the last root, that is the c sub n, e raised to mn times x. So wherein basically the value of c are the arbitrary constants. So let's have an example for this case. Homogeneous linear equations with constant coefficients. With the auxiliary equation for distinct roots. So let's have this example. Number 1. I determine the general solution of the quantity 3 times d cubed y over dx cubed, that is the third derivative, plus 5 multiplied by d squared y over dx squared, second derivative, minus 2 dy over dx. So first derivative multiplied by y. So this is already in the form of a linear homogeneous differential equation with constant coefficients. So all we have to do is we may rewrite this expression in the form of f of d multiplied by y equal to 0. That is our differential operator. So we are rewriting this expression. Let's say that is 3 times d cubed y over dx cubed is third derivative. So 3 times the differential operator d cubed, and then plus 5 d squared y over dx squared is second derivative. So multiplied by 5d, the 5d squared ay minus 2 dy over dx, first derivative, 2 times d. So this ay quantity ay multiplied by y equal to 0. So let's have the auxiliary equation. So for the auxiliary equation, that is f of m is equal to 0. Basically, we are just to replace the differential operator. I replace them with m. So we can have it as 3 times m cubed plus 5 d squared minus, we are replacing d with m. So 5 times m squared minus 2m is now equal to 0. So we replace all d with m. So this will be our auxiliary equation. So let us determine the roots. Hopefully they are real and distinct. Since again, this auxiliary equation is applicable for distinct roots. So I'll be just using the mode equation of the calculator. So this is mode equation number 4. That is, we have 3, 5, negative 2, then 0. So we have the first root is 1 over 3, negative 2, then 0. So let's have the roots. So I'll be starting with, let's say, m1. I'll be starting with the 0. The second root is, what is that value again? 0, 1/3, 0, negative 2. Then let's say the third root is 1, 1/3. So these are the roots. 0, 1/3, negative 2, then 0. So we are now to write our general solution. So again, what is our general solution? So we can write the general solution at once. That is, the y is equal to c1 e raised to m1 times x, plus the c2 is e raised to m2 times x. So we have 3 roots. So let's say plus c sub 3 e raised to the m sub 3 multiplied by x. So we are now to substitute. We have y is equal to c1 e raised to is our first root. So I place 0. That is 0 times x plus c sub 2. This is e raised to, this is negative 2 times negative 2 times x plus we have c sub 3. This is e raised to m sub 3 is, that is 1/3 multiplied by 1/3 multiplied by x. So we are now just to simplify. We have y is now equal to, so this term, any value raised to 0 is the same as 1. So this y is now equal to c1 plus c sub 2. This is e raised to negative 2 multiplied by x plus we have c sub 3. This is e raised to 1/3 of x. So this will be the general solution of our first example. The general solution of this linear homogeneous differential equation. So y is equal to c1 plus c2 multiplied by e raised to negative 2x plus c sub 3 e raised to 1/3 of x. So that will be our first example. So let's have another example. So we proceed to the second example. This is d squared x over dt squared minus 4x equal to 0 when t is equal to 0, x equal to 0, and dx over dt is equal to 3. So this time, our independent variable is t and dependent variable is x. So from our previous example, we are using the expression y is equal to e raised to m times x. But since for this example, we are using different variables. So our dependent value is x. This is x is equal to e raised to m multiplied by t instead of y. So this will be our equivalent expression. By x equal to e raised to m t. Since we are using a different variable. So we are to use a different approach for this example. So instead of using the differential operator d, so I'll be giving the equivalence of the first derivative of this expression. That is, the first derivative will be the dx is equal to, what is the derivative of e raised to mt? If we are to recall our differential calculus, that is the derivative of e raised to u is simply equal to e raised to u du. So therefore, this will be e raised to mt, m is constant, times t, the variable, that is multiplied by m times dt. So we'll be having the equivalent of the dx divided by dt is now equal to m multiplied by e raised to m times t. That will be the equivalent of the first derivative. But we need the second derivative since that is d squared x over dt squared. So we are now to take the second derivative. The derivative of the dx divided by dt is now equal to m. All we have to do is repeat the process. E raised to mt, what is the derivative of e raised to mt is m dt. So we are now to simplify. This is now for the second derivative. This is now d squared x divided by dt times dt. That is the dt squared is equal to m times m. That will be m squared e raised to m times t. That will be the equivalent of the second derivative. So we have now the equivalent of x. The first derivative, dx over dt. Second derivative, the d squared x over dt squared. So let us substitute to our original equation or our initial equation. So the initial equation is our initial equation, that is the d squared x, this is divided by dt squared minus 4x is now equal to 0. What is the equivalent of d squared x over dt squared? So we have that as, we have m squared e raised to m times t minus, this is 4. What is the equivalent of x? The equivalent of x is the e raised to m times t. So it's 4 times e raised to m times t equal to 0. So dividing all terms with e raised to mt, so we are to cancel these terms. So 0 divided by e raised to mt is the same as 0. So we'll be having our auxiliary equation as the m squared minus 4 is simply equal to 0. So this will be easy. So we have to do is transpose. So m squared is now equal to 4. Then we are to take the square root. So what is the square root of 4 is simply equal to a positive or negative 2. So we can conclude that the roots, let's say m1, I'll be using m1 as negative 2. The second root, m2, will be the positive 2. Then we are now ready to write our general solution. So for the general solution, so again, instead of using y, we are using x is equal to the first root, c1 e raised to m1 times, instead of x, we are using t. So x equal to c1 e raised to m1 times t. Then for the second, this is c sub 2 e raised to m2, the second root, multiplied by t. So for our general solution, all we have to do is I substitute. This is now x is equal to c1. This is e raised to negative 2 times t. So since our m1 is negative 2, okay, then plus, we have c sub 2. This is e raised to positive 2 times t. So this will be the general solution, or the equation of the general solution. But since we have an additional given, that is at time is equal to 0, we have dx over dt is equal to 3. So we can also determine the particular solution for those given. So we are to substitute the values. We have at time is equal to 0. We have the value of x is also equal to 0. So substituting, the value of x is 0 equal to c1. This is e raised to negative 2 times 0 plus c sub 2. This is e raised to positive 2 times t is also equal to 0. So we know the values. Raised to 0 is the same as 1. So we'll be having our first equation. This is now 0 equal to c1 plus c2. So we can have an equivalent, let's say c sub 2 transpose, that will be negative. C sub 2 is equal to negative c sub 1. This is our first equation. We are now to use the other given, that is the dx over dt is equal to 3. So we have, the value of t is equal to 0. The value of the dx over dt is equal to 3. So therefore, from our general solution, or the equation of the general solution, we need to take the first derivative to have the term, the dx over dt. So this is dx is equal to c1. What is the derivative of e raised to negative 2t? That is simply negative 2 dt. Then plus, what is the derivative of, this is c sub 2 e raised to 2t. What is the derivative of e raised to 2t? That is simply 2 times dt. E raised to 2t times 2 dt. So dividing all terms with dt, this will give us on a term on the left side. That is the dx over dt is now equal to, this will be negative 2c1 e raised to negative 2t, then plus, this is 2c sub 2 e raised to positive e raised to positive 2t. Then we are now to use these values. At t is equal to 0, the dx over dt is equal to 3. So this will be 3 equal to negative 2 c1 e raised to negative 2 times 0, then plus 2 times c sub 2. This is e raised to 2 times 0. But these values, e raised to 0 is the same as 1. So we'll be having our equation. This is 3 equal to negative 2c1, plus 2c sub 2. And then we may now substitute the equivalent of c sub 2 from our equation 1 to this second equation. This is 3 is now equal to negative 2 c1 plus twice of, what is c sub 2? That is negative c1. So we have negative plus negative. This is 3 is equal to negative plus, negative 2 plus negative 2 is negative 4 of c1. So dividing both sides of the equation by negative 4, this will give us the equivalent of c1 as the negative 3 over 4. Then what will be the value of c sub 2, our second arbitrary constant? The C sub 2 is equal to negative C1, negative 3 over 4. So we will be having the C sub 2 is equal to positive 3 over 4. So as you can see, they are numerically equal but opposite in sign. We have now the value of the arbitrary constants, so we can now write our particular equation or the specific solution. So the particular solution of that higher order differential equation so for the particular solution, so from our general solution, x equal to c1 e raised to negative 2t plus c2 e raised to 2t. We are now to substitute the value of the arbitrary constants. This is x is equal to c1. What's the value of c1? That's negative 3 over 4 multiplied by e raised to negative 2t, then plus the value of c2, that is 3 over 4, e raised to positive 2t. So we have this is the particular solution based on the given. We have 3 over 4 e raised to positive 2t, then minus 3 over 4 e raised to negative 2t. I just disarranged the two terms on the right side of the equation. So this will be the particular solution of the given higher order differential equation with this given t is equal to 0, x equal to 0, and dx over dt is equal to 3. So these are our solutions, the general solution and the particular solution. So this will be our solution for example number 2.